My name is Hemantha. My registration number is MS25941562. Today I will demonstrate an exact method solution for capacitated vehicle routing problem CVRP using integer linear programming. Our objective is to find the mathematically shortest set of routes for a fleet of vehicles while adhering to strict capacity limits. While many real-world logistic problems use heuristic, this ILP model provides a probable optimal solution for our defined subset. So it is important to note that we are using an exact method, unlike heuristic, which find a good solution, and ILP model explores the entire solution space to guarantee the global optimum. This makes it the benchmark for accuracy in optimization tasks. Okay, now let's go through the data set here. What I have used. Let's look at the data source. The data source is X N101K25 benchmark dataset. In the raw file, we have coordinates for 100 customers here, and one central report. So this first node is the report. The most critical constraint here is the vehicle capacity, which is set to 206 unit, because its total demand across customers exceeded this 206 unit limit. Our model is forced to split the work across multiple vehicles rather than one single path. The key takeaway here is the capacity to demand ratio. In this specific dataset, demand of our subset is nearly 3 times the capacity of single truck. This mathematically necessitated at least 3 distinct routes, which adds a layer of complexity beyond the standard traveling salesman problem. Okay, let's move to the mathematical formulation here. What I have used to solve this, I have implemented the Miller truck assignment MTC formulation. We use a binary decision variable called xij to represent the paths between nodes, and the secret to this model is the auxiliary variable ui, which tracks the commutative load of the trucks and each stop. This ensures two things. First is prevent subtours or illegal loops, and the second, it guarantees the vehicle never carries more than its 206 unit limit. The MTC constraints are a classic solution to the sub2 elimination problem. Without these, the solver might suggest floating loops that never return to the report. By linking the load vehicle UI to the moment variable xij, we forces a logical canonical flow for every vehicle. Let's move to the subset strategy and complexity of here. So because of ILP is an exact method, its computational complexity grows quadratically or n square. To demonstrate the solver precision within the practical time frame, I have configured this model for an n subset of 20 customers. This 21 node, probably including now this 20 customers, but there's another node for depot that provides a significant challenge for solving while allowing us to reach the guaranteed global optimum demonstration. Now in here I have set it the subset as 20 here. The reason we limit n is due to NP hardness. In an ILP, doubling the number of nodes doesn't just double the work, it increases the search space exponentially. By choosing 20 customers, we maintain a balance where the problem is still complex enough to be meaningful, but small enough to solve the optimality in minutes. Okay, now let's move to the multi-vehicle constraints here. Now in here I have set the max vehicles. Now each constraint section I handle the multi-vehicle logic. Since the demand for these 20 customers is over 600 unit, a single truck is physically impossible. So I implemented logic allowing to depot to send out up to 5 vehicles. Every customer node must be visited exactly once, but the depot can have multiple departures to satisfy to total demand. Uh, Crucially, the model is provide agnostic reading the fleet. We don't pre-assign which truck goes where. The solver determines the number of vehicles used in case these three, based purely on what minimize total distance while staying under the 206 unit cap. So so after we done that, so now since this problem is optimal solution here, um, I utilize the CBC solver with 5% native gap. uh, I have mentioned it here. um, uh, I utilized I utilize CBC solver with 5% native gap tolerance. As you can see, the solver successfully reached the status optimal here. Mm, this represents the absolute shortest distance possible for the subset. Looking at the visualization, you can see the results. Uh, the solver has the guaranteed distinct blue loops. Each route efficiently serves a bl- except not only the blue loop, red, blue, and other color multicolor loops. Um, each route efficiently serves a group of customers and return to the depot without ever exceeding the 206 unit capacity. Notice the optimal status here. Uh, this confirms the duality gap has been closed. Uh, in the plot, clustering efficient is visible. The solver naturally grouped customers who are geographically chosen to minimize the Euclidean distance, proving that the objective function is working correctly. So finally, uh, in conclusion, this project highlight the precision of exact methods. While ILP is gold standard for small scale routing, and NP hard nature of CVRP means that the full 101 node dataset meta heuristics meta heuristic like the genetic algorithm are necessary. This model, however, provides the necessary benchmark for understanding what a perfect solution looks like. Uh, so, the major takeaway is the precision scalability trade-off. We use ILP when we need the absolute best answer, and and have limited nodes. We used heuristic when we have hundred of nodes and need an answer quickly. Understanding when to use each is the hallmark of professional optimization engineer. So that is about the ILP method optimization. So thank you for your time.